June 6, 1944. Dawn breaks over the Normandy coast as the largest amphibious invasion in human history unfolds across 5 beaches. German commanders watching from fortified positions witness an unprecedented spectacle. Thousands of ships stretching to the horizon, aircraft filling the sky, men and machines pouring onto French soil. But what they observe in those first chaotic hours is merely the opening act. Within days, they will witness something that defies every principle of military engineering they have ever known. The Allies are going to build 2 complete harbours, each larger than Dover in open water, under fire, in just over a week. The concept seems impossible. Harbours are permanent installations requiring years of construction, protected waters, massive concrete foundations sunk into bedrock. The Normandy coast offers none of these advantages. Steep beaches, powerful tides rising and falling 20 feet, brutal channel storms and German guns covering every approach. Yet Allied engineers are about to construct artificial harbours capable of unloading 12,000 tons of supplies daily, complete with floating piers, breakwaters and roadways, all built from prefabricated components towed across 100 miles of open ocean. The story of the Mulberry Harbors represents one of the most audacious engineering achievements in military history. It begins not with triumph, but with tragedy, and the hard lessons learned from a disastrous raid 2 years before D-Day. August 19, 1942, the port of Dieppe, France. Operation Jubilee, a raid intended to test German coastal defences and gather intelligence, becomes a bloodbath. Of the 6,086 men who land, primarily Canadian forces, 3,623 are either killed, wounded, or captured within 9 hours. The Germans, forewarned and prepared, turn the port into a killing ground. But beyond the human cost, the raid reveals a fundamental problem for any future invasion of Europe. Taking a defended port is nearly impossible, and holding it long enough to sustain an invasion is even harder. Vice Admiral John Hughes Hallett, one of the planners observing from offshore, watches the disaster unfold and reaches a conclusion that will reshape Allied strategy. If we can't capture a port, we must bring one with us. This radical idea, dismissed as fantasy by many senior officers, eventually reaches the desk of Winston Churchill, who scrawls in the margins of a planning document. Piers for use on beaches. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the difficulties. The difficulties will argue for themselves. Churchill's vision is not entirely original. During World War I, he had proposed similar floating harbours for operations in the Baltic. But in 1942, the technology to build such structures barely exists. What follows is one of the most intensive engineering development programs of the war, conducted in absolute secrecy, racing against a deadline that cannot be missed. The challenge facing Allied engineers is unprecedented in scale. They must design harbour facilities that can be prefabricated in Britain, survive a 100-mile tow across the English Channel, be assembled in waters up to 80 feet deep, withstand channel storms, accommodate the extreme tidal range, and begin operations within days of D-Day. These harbours must handle the cargo of dozens of ships simultaneously, unloading everything from tanks to ammunition, fuel to food, all while under potential German artillery fire and air attack. The scale alone is staggering. Planners calculate that the invasion force will require 12,000 tons of supplies daily just to sustain operations. This includes 2,500 vehicles, 20,000 tons of fuel, and mountains of ammunition, food, medical supplies and equipment. Without port facilities, everything must come across open beaches, vulnerable to weather, tides and German counterattacks. History offered no encouraging precedents. Every major amphibious operation had required the immediate capture of port facilities. In early 1943, a special design team is assembled under Brigadier Bruce White, a brilliant engineer with experience in dock construction. His team includes naval architects, civil engineers, scientists from the National Physical Laboratory, and representatives from major British construction firms. They work in converted country estates, requisitioned warehouses, and secret facilities scattered across Britain. Security is so tight that many team members don't know what their colleagues are building. Each component is designed in isolation, the full picture known only to a handful of senior planners. The basic concept that emerges involves 3 primary elements. First, breakwaters to create calm water for unloading. Second, floating piers that rise and fall with the tide while remaining connected to shore. Third, floating roadways allowing vehicles to drive from ships directly onto the beach regardless of tide level. Each element requires solving engineering problems that have never been addressed before. The breakwater solution takes several forms. The primary protection will come from massive concrete caissons, each one a 5-story tall floating structure weighing up to 6,000 tons. These Phoenix caissons, as they're codenamed, are designed to be towed across the channel, then deliberately sunk in position to create a permanent barrier against waves. The engineering is elegant in its simplicity. Each caisson is a hollow concrete box subdivided into compartments. With compartments flooded to specific levels, the caisson floats just high enough for towing. On arrival, valves are opened, the structure settles onto the seabed, and compressed air is blown into selected compartments to bond the caisson firmly to the bottom. But building these monsters presents enormous challenges. Each caisson requires 4,000 tons of concrete and 350 tons of steel reinforcement. They must be constructed in dry docks, launched without damage, kept afloat during towing, and positioned with precision on the Normandy seabed. The concrete must cure for months to achieve full strength, meaning construction must begin more than a year before D-Day. And all of this must happen without the Germans learning what these mysterious structures are for. Construction sites are established in shipyards, dry docks, and specially excavated basins along Britain's coast. Workers building the caissons are told they're constructing fuel storage tanks, underwater oil containers, or ammunition magazines. Anything to hide their true purpose. The work proceeds around the clock. Concrete is poured continuously using techniques borrowed from dam construction. Steel reinforcement is woven into complex patterns designed to withstand not just wave pressure, but also the shock of settling onto potentially uneven seabeds. The largest caissons, designated Phoenix A1, measure 200 feet long, 56 feet wide, and 60 feet high. They displace more water than a small freighter and require specialized tugs to tow them. Each caisson's interior is subdivided into 17 separate compartments, with individual flooding valves, pumps, and compressed air systems. Anti-aircraft guns are mounted on the tops, turning these floating fortresses into defensive positions once in place. Parallel to caisson development, engineers work on an even more unusual breakwater concept. 55 obsolete warships and merchant vessels, dubbed corncobs, will be towed to Normandy and deliberately scuttled to form additional breakwater protection. These block ships range from elderly battleships to liberty ships damaged beyond economic repair. Each vessel is prepared with explosive charges, positioned to ensure it settles properly when sunk, creating maximum wave protection while not blocking harbour access. The floating pier design proves equally challenging. The whale pier system must allow ships to unload directly onto roadways that remain horizontal, regardless of tide level. The solution involves massive floating steel bridges supported by 90-foot tall steel towers called spuds. These spuds rest on the seabed but are not anchored. Instead, they simply support the pier through their weight and friction. As the tide rises and falls 20 feet twice daily, the pier decking slides up and down the spud towers on bearing systems, remaining level while adjusting to the water height. Each whale pier section is 200 feet long and 60 feet wide, built from standard Bailey Bridge components modified for marine use. The roadway can support 40-ton tanks and heavy trucks. The spuds, hollow steel tubes 15 feet in diameter, must be precisely positioned on the seabed and remain stable against powerful tidal currents, wave action, and the weight of loaded vehicles. The engineering tolerances are incredibly tight. If a spud shifts even a few feet, the entire pier section becomes unusable. The third element, the floating roadways connecting piers to shore, requires solving another unique problem. These whale pontoons must flex with wave action, while providing stable roadway for vehicles, handle the full tidal range, and remain connected during storms. The solution is a series of hinged floating sections, each 80 feet long and 40 feet wide, connected by universal joints allowing movement in 3 dimensions. The roadway surface is steel grating providing traction, while allowing wave water to pass through, reducing forces on the structure. By late 1943, prototype testing begins in Scottish sea locks, where tides and weather approximate Normandy conditions. The tests reveal numerous problems. Caissons prove difficult to control during towing, requiring specialized bridle arrangements and multiple tugs. Whale pier spuds tend to sink into soft seabeds, requiring the addition of massive concrete foundation pads. The floating roadway hinges fail under heavy loads until engineers strengthen them with massive steel pins. Each problem requires solution, modification of hundreds of already built components, and additional testing. Production accelerates through winter 1943-48. Across Britain, over 45,000 workers are building harbour components, most still unaware of their true purpose. The concrete caissons alone require 330,000 cubic yards of concrete and 31,000 tons of steel. The whale piers need 150,000 tons of steel components. Specialized vessels must be built just to tow the massive structures. The scale of production rivals that of building multiple battleships, all completed within months, while Britain is simultaneously building aircraft, tanks, ships, and weapons. The logistics of storing and concealing thousands of harbour components become a nightmare. The caissons are too large to hide, so they're dispersed to dozens of anchorages and described as fuel storage or ammunition containers. Whale sections are stored in rivers, estuaries, and coastal inlets, covered with camouflage netting. German reconnaissance aircraft photograph many components, but intelligence analysts, unable to imagine their true purpose, classify them as storage facilities or construction material. Security measures border on paranoia. Workers sign the Official Secrets Act, forbidden from discussing their work even with family. Mail from construction sites is censored. Movement in and out is restricted. German intelligence receives reports of massive construction projects, but pieces together only fragments. A February 1944 intelligence summary mentions concrete structures of unknown purpose in British ports, but concludes they're probably breakwaters for harbour expansion. The true test comes in April 1944 when components begin assembling for the Channel crossing. This movement, involving hundreds of tugs and thousands of individual floating sections, cannot be concealed. The Allies gamble that German intelligence will not deduce the purpose in time to prepare adequate countermeasures. It's a gamble that pays off. German commanders observe the massive assembly, but conclude the Allies are gathering invasion equipment, not suspecting the structures themselves are the port facilities. On June 6, 1944, as Allied troops storm ashore, the first corncobs, the block ships, are already being towed toward Normandy. Within 24 hours of the initial landings, elderly warships and merchant vessels are being positioned off Omaha and Gold Beaches. HMS Centurion, an old battleship that fought at Jutland in 1916, is among the first, scuttled in 50 feet of water to begin forming the breakwater. Over the next 3 days, 55 vessels are positioned and sunk, creating the first line of protection for what will become harbours named Mulberry A off Omaha Beach and Mulberry B off Arromanches. The scuttling operations proceed with remarkable precision. Each block ship has been prepared with explosive charges positioned by demolition experts. As ships reach their designated positions, coordinates verified by survey teams, the charges are detonated. The vessels settle onto the seabed within minutes, positioned to overlap and create maximum breakwater effect. German observers watching from shore positions report the sinkings to headquarters, still not comprehending what they're witnessing. One report describes it as the Allies disposing of damaged vessels by scuttling them offshore, a curious choice that merely creates obstacles to navigation. Within 48 hours, Phoenix caissons begin arriving. The towing operation is one of the largest maritime movements in history. Over 400 separate tows, each involving massive concrete structures weighing thousands of tons, cross the channel in carefully coordinated convoys. The caissons, floating with just a few feet of freeboard, are vulnerable to rough weather. Towing speeds average just 4 knots, slower than a man's walking pace. The crossing takes 18 to 30 hours depending on tow speed and weather. Each caisson is escorted by multiple tugs, with specialized crews aboard monitoring ballast and stability. German coastal artillery begins engaging the structures as they're positioned, but the sheer number of targets overwhelms defenders. Shells that hit caissons often pass through, without exploding, the hollow interiors offering little resistance. Some caissons are damaged, settling improperly or suffering structural failure, but the majority are positioned successfully. Survey teams mark exact positions using bearings from shore reference points. Divers inspect seabeds before placement, clearing obstacles. Caisson commanders, Royal Navy officers specially trained for this operation supervised the flooding sequences that settle each massive structure onto the bottom. The scene offshore Normandy in those first days after D-Day is unlike anything in military history. Hundreds of ships anchor in waters partially protected by block ships. Phoenix caissons are being positioned in precise patterns, their tops bristling with anti-aircraft guns. Whale Pier. Sections are being assembled, the massive spud towers being lowered into position by floating cranes. German spotters report to headquarters that the Allies are building something in the water, but intelligence officers struggle to understand what they're seeing. On June 9th, German commanders finally realize the truth. A Luftwaffe reconnaissance aircraft photographs Mulberry B under construction at Arromanches, and photo interpreters identify pier structures, floating roadways, and the systematic arrangement of caissons. The report sent to Army Group B headquarters describes artificial harbour facilities being assembled from prefabricated components. Field Marshal Erwin Rommel, commanding German forces in Normandy, immediately recognises the implications. If the Allies can build functioning ports independent of capturing existing facilities, the entire German defensive strategy collapses. Rommel orders concentrated attacks on the harbour construction. Luftwaffe bombers brave overwhelming Allied air superiority to attack the caissons. E-boats, fast German patrol craft, attempt night raids. Coastal artillery that can range the harbour's fires day and night. But the defences are formidable. Hundreds of anti-aircraft guns mounted on caissons, destroyers and shore batteries create a virtually impenetrable screen. The few German aircraft that penetrate are shot down before reaching targets. E-boat attacks are driven off by destroyers and motor torpedo boats. Artillery shells, while numerous, cause only scattered damage. By June 12th, 6 days after D-Day, the first whale piers are operational. Ships begin unloading directly onto the piers, vehicles driving off onto floating roadways and proceeding to shore without touching water. The efficiency compared to beach unloading is dramatic. A Liberty ship that might take 12 hours to unload across a beach can discharge its cargo in 4 hours at the pier. Throughput begins approaching the planned 7,000 tons daily per harbour. The engineering challenges of operating the harbours prove as significant as building them. The tidal range of 20 feet means pier sections rise and fall dramatically. The spud towers experience immense forces as loaded vehicles cross during tidal currents. Maintenance crews work constantly, adjusting bearings, replacing damaged sections, repairing storm damage. The floating roadways, while ingeniously designed, require constant attention as hinges wear and sections work loose. German artillery becomes the most persistent threat. Long-range guns positioned miles inland can reach the harbours, firing harassment barrages that damage ships and facilities. One caisson at Mulberry suffers a direct hit that floods compartments, causing it to list but not collapse. Repair crews patch the damage using underwater concrete, literally diving into the flooded compartments to seal shell holes. The caisson remains in position, a testament to the robust engineering. On June 19th, disaster strikes. A severe storm, the worst June weather in the Channel in 40 years, hits Normandy with winds gusting to 45 miles per hour and waves reaching 8 feet. The storm lasts 3 days, testing every element of the harbour design beyond its limits. At Mulberry A off Omaha Beach, the more exposed of the two harbours, caissons begin breaking loose. The anchoring systems, designed for normal storm conditions, cannot hold against the sustained battering. Floating roadways tear apart at their hinges, sections driven ashore or sunk. Several Phoenix caissons, improperly settled due to rushed initial placement, topple over as seabeds erode beneath them. The damage to Mulberry A is catastrophic. When the storm clears on June 22nd, the harbour is essentially destroyed. Over 800 vessels have been driven ashore or damaged. The whale piers are wrecked, spud towers toppled or bent. Only the Phoenix caissons that were properly seated remain functional, still providing breakwater protection, but no longer supporting a working harbour. General Omar Bradley, commanding American forces at Omaha, surveys the wreckage and estimates 2 months will be needed to rebuild. But Mulberry B at Arromanches, partially sheltered by geography and more carefully constructed, survives with repairable damage. British engineers immediately begin salvage operations, recovering usable sections from Mulberry A and reinforcing Mulberry B. The decision is made not to rebuild the American harbour, but instead to expand and strengthen the British one, while improving beach unloading techniques at Omaha. German intelligence officers studying reconnaissance photographs after the storm report that the Allied artificial harbour has been destroyed by weather, proof of the inherent folly of the concept. They predict the Allies will now be forced to capture Cherbourg immediately or risk logistical collapse. But Allied planners, while frustrated by the loss of Mulberry A, adapt. Beach unloading techniques are improved, utilising lessons learned from harbour operations. Specialised vehicles, amphibious trucks, and improved coordination allow continued build-up despite the harbour loss. At Arromanches, Mulberry B is not just repaired, but significantly expanded. Additional Phoenix caissons are towed from Britain, positioned to extend breakwater protection. Whale piers are reinforced with extra spud towers, reducing stress on individual supports. The floating roadways are modified with stronger hinges and additional support pontoons. By early July, Mulberry B is handling over 7,000 tons daily, approaching pre-storm levels. The logistics flowing through the surviving harbour are staggering. A typical day sees 40 coasters, small cargo vessels of 1,000 to 2,000 tons, unloading simultaneously. Each disgorges tanks, trucks, ammunition, fuel, food, and every conceivable supply needed by armies advancing inland. The pier roadways see continuous traffic, vehicles rolling off ships, across floating bridges, onto shore roads without stopping. Time motion studies show the harbour achieves unloading rates comparable to major peacetime commercial ports, a remarkable achievement for a facility built under fire from prefabricated components. German commanders watching this logistical miracle unfold realize they're witnessing military innovation that renders traditional strategy obsolete. General Günther Blumentritt, Chief of Staff to Field Marshal von Kluge, later writes, "The artificial harbours were the single greatest surprise of the invasion. We had anticipated every Allied capability except this one. In one stroke, they solved the fundamental problem of amphibious warfare, eliminating our assumption that we could contain any landing by holding port facilities. The psychological impact on our commanders was severe. If the Allies could build harbours from nothing, what other miracles might they achieve?" The technical achievements of the Mulberry Harbors extend beyond the structures themselves. The logistics of supplying the harbour components required detailed planning rivaling the invasion itself. Over 600 tugs were assembled for towing operations. Specialised crews, thousands of seamen trained in handling massive floating structures, were recruited and trained. Navigation systems using shore-based radio beacons allowed precise positioning in all weather. Communication networks coordinated movements of hundreds of vessels simultaneously. The materials science alone represented cutting-edge engineering. The concrete used in Phoenix caissons was a special rapid hardening formula that achieved 70% strength in just 28 days versus the normal 90 days for marine concrete. Steel components were treated with specialized coatings to resist saltwater corrosion. The anti-aircraft mountings atop caissons required vibration damping systems to remain stable during firing, while the caisson flexed under wave action. Every element required innovation beyond existing practice. By August 1944, Mulberry B has handled over 628,000 tons of supplies, 40,000 vehicles, and 220,000 troops. These figures represent the logistics required to sustain 39 Allied divisions advancing across France. Without the harbour, this build-up would have been impossible. The Germans, forced to move only at night to avoid Allied air attack, watch as the Allies demonstrate complete logistical dominance enabled by their artificial port. The harbour continues operating through fall 1944, even as Allied armies capture actual ports. Cherbourg is taken in late June but requires weeks of repair work to clear German demolitions. Le Havre falls in September but is equally devastated. Through this period, Mulberry B remains the primary supply point, more reliable than the damaged permanent ports. It handles heavier tonnage than any other single port facility in the European theatre during summer 1944. The operational lifespan of Mulberry B far exceeds design specifications. Originally planned to function for 3 months, providing initial build-up capacity until permanent ports could be captured and repaired, the harbour operates continuously for 10 months. It's still in limited use in November 1944 when autumn storms finally inflict damage beyond field repair capability. By then, Antwerp has been captured and cleared, providing the deep water port facilities needed for final operations into Germany. The costs of building the Mulberry Harbors were enormous, but must be viewed in context. the total construction consumed resources equivalent to building 20 major warships, employed 45,000 workers for months, and cost approximately £40 million, about $2 billion in current value. But this expenditure enabled the Normandy invasion to proceed without the necessity of immediately capturing a fortified port, likely saving thousands of lives and months of time. German defensive planning had assumed port facilities would be the critical bottleneck limiting Allied operations. They heavily fortified Cherbourg, believing its capture would be necessary within days of any landing, and that defending the port would allow time to bring up reserves and contain the invasion. The Mulberry Harbors rendered this strategy irrelevant. Allied forces could build up faster than Germans could reinforce, establishing a numerical advantage that proved decisive. Post-war analysis by German officers invariably cites the artificial harbours as one of the war's most significant surprises. General Blumentrit's assessment captures the consensus view. We had excellent intelligence on Allied equipment, training and doctrine, but the Mulberry Harbors represented thinking beyond our conceptual framework. The idea of building port facilities as a prefabricated, mobile system never occurred to us. When we finally understood what the Allies were doing, we realised we were facing an enemy with not just material superiority, but conceptual superiority. They had reimagined the fundamental problems of warfare. The engineering innovations pioneered for Mulberry influenced post-war harbour and offshore construction. Floating production platforms, prefabricated harbour facilities for rapid deployment, and modern ship-to-shore cargo handling systems all trace concepts back to the Normandy harbours. The principle of designing complex systems as assemblies of prefabricated, transportable modules became standard in offshore engineering. Several Phoenix caissons remain visible off Arromanches today, massive concrete blocks still sitting where they were positioned in June 1944. They're popular dive sites, artificial reefs colonised by marine life, physical remnants of one of engineering's greatest achievements. The French government has protected them as historical monuments, banning any salvage or damage. The human stories behind the harbours are equally remarkable. The construction workers who built components without knowing their purpose, maintaining security despite the obvious importance of their work. The tug, crews who shepherded massive caissons across the channel in hazardous conditions. The divers who positioned caissons working in dark, cold water under constant time pressure. The maintenance crews who kept the harbours functioning despite storm damage, shell fire and equipment wear. Each group contributed to an achievement that changed warfare. One particularly moving account comes from a British seaman who helped sink blockships off Omaha Beach. His elderly destroyer, HMS Vindictive, had fought at the Zebra grade in 1918, been scuttled there as a blockship, later salvaged and returned to service. In 1944, the ship was selected for its final mission, to be sunk again as a blockship, this time off Normandy. The crew, many of whom had served aboard for years, prepared the ship with special care. They removed personal items, cleaned and painted her, and when the time came to scuttle, held a brief ceremony. As the ship settled onto the Normandy seabed, the last captain remarked that she was finally at rest after serving in both world wars, her final service helping to ensure this war's outcome would be different. The scale of Allied deception that protected the Mulberry Project until D-Day deserves recognition. German intelligence monitored British ports, observed construction activity, photographed structures. But the cover stories, the dispersal of components, the mundane explanations given for each element, successfully concealed the whole until too late for effective countermeasures. This operational security, maintained across tens of thousands of workers for over a year, represents a counterintelligence success as significant as the engineering achievement. The Mulberry Harbors demonstrated that with sufficient engineering skill, industrial capacity and coordination, military forces could overcome natural obstacles previously considered insurmountable. The Normandy coast, with its difficult beaches, extreme tides and lack of ports, had been viewed as defensible precisely because of these natural barriers. The artificial harbours transformed the problem, creating the necessary infrastructure through human ingenuity rather than capturing it through battle. In June 1945, with victory in Europe secured, a detailed assessment of factors contributing to Allied success listed the Mulberry Harbors among the top 10 decisive elements, alongside the atomic bomb program, radar development, and code-breaking efforts. General Eisenhower, in his memoirs, wrote, "The artificial harbours were a brilliant conception. Their construction and operation represented one of the war's great technical achievements. History will likely judge them as the key that unlocked the fortress Europe. The final word perhaps belongs to Admiral Bertram Ramsay, the Allied naval commander who oversaw Mulberry construction and operation. In a letter to the British War Cabinet in August 1944, he wrote, "When historians examine this campaign, I believe they will conclude that our greatest achievement was not in the fighting, courageous though it was, but in our engineering. We transported an army across defended water, landed it on hostile shores, and sustained it there without use of port facilities by building our ports from prefabricated components. This required imagination, planning, industrial capacity, and execution at levels never before achieved. The Germans were shocked because they could not imagine such a thing possible. Their shock was justified. What we accomplished was, by any previous standard, impossible." The Mulberry Harbors represent the ultimate expression of American and British industrial warfare. They combined engineering innovation, manufacturing capacity, logistical coordination, and operational skill into a single integrated system that solved a problem Germans believed insoluble. When German commanders first witnessed ships unloading at artificial piers built from nothing in days, their shock was not merely surprise but the realization that they were fighting enemies capable of reimagining warfare itself. The harbours didn't just help win the battle for Normandy, they demonstrated the futility of German resistance against powers that could literally build infrastructure from nothing while under fire. The thunder of waves against Phoenix caissons sounded the death knell for the Third Reich. The engineering lessons learned from Mulberry informed not just harbour construction, but every aspect of military logistics for decades to come. Within weeks of D-Day, American and British engineers were analysing performance data, documenting failures, and identifying improvements. The storm damage to Mulberry A, while devastating operationally, provided invaluable data on structural loads, anchoring systems, and failure modes that would have taken decades to accumulate in peacetime testing. One critical discovery involved the behaviour of Phoenix caissons in extreme conditions. Engineers had calculated wave forces based on historical channel weather data, but the June storm produced wave patterns that exceeded worst-case predictions. Analysis revealed that caissons positioned in certain orientations created resonance effects, amplifying wave forces beyond design limits. This led to new understanding of wave dynamics in shallow water that influenced all subsequent offshore structure design. Post-war harbour construction worldwide incorporated these lessons, potentially preventing countless structural failures. The whale pier system similarly revealed unexpected behaviour. The spud towers, those massive steel tubes supporting the floating decks, experienced stress concentrations at their bases that design calculations had underestimated. Several towers developed cracks that could have led to catastrophic failure if not discovered during routine inspections. Maintenance teams developed emergency repair techniques, including underwater welding and reinforcement sleeve installation, that became standard practice into offshore construction. These improvised solutions, born of necessity under combat conditions, advanced marine engineering practices by years. The floating roadway sections demonstrated both remarkable resilience and unexpected vulnerabilities. The hinged connections, designed to flex with wave action, performed brilliantly in normal conditions but proved susceptible to harmonic oscillation during certain wave frequencies. Engineers observed that when waves matched the natural frequency of roadway sections, oscillations would build until hinges failed or pontoons capsized. The solution involved adding damping systems, essentially massive shock absorbers that disrupted harmonic buildup. This principle of tuned mass damping is now standard in bridge design and high-rise construction. Beyond structural engineering, the Mulberry project revolutionized construction project management. The coordination required to build thousands of components at dispersed sites, transport them to assembly areas, and install them in precise sequence under combat conditions demanded new organizational methods. Critical path analysis, though not yet formalized under that name, was employed intuitively. Project managers identified which components were bottlenecks and allocated resources accordingly. This experience directly influenced post-war development of project management as a formal discipline. The logistics of the Mulberry towing operation alone represented an unprecedented achievement in maritime coordination. Over 400 major structures, each requiring specialized handling, had to cross the channel in specific sequence to allow proper harbour assembly. A caisson arriving before its position was surveyed and marked was useless, potentially even an obstacle. Whale pier sections needed to arrive after breakwaters provided protection, but before supply ships began massing offshore. The coordination involved weather forecasting, tide tables, vessel performance characteristics, and construction sequence requirements integrated into a master schedule of stunning complexity. Weather forecasting, still a primitive science in 1944, became critical to Mulberry operations. The June storm that devastated Mulberry A had been predicted only 18 hours in advance, insufficient time to secure floating structures adequately. This experience drove military investment in meteorology that transformed the field. The network of weather stations, reconnaissance aircraft, and analysis centres built to support the invasion became the foundation for modern weather forecasting. The lesson that accurate weather prediction could prevent losses exceeding the cost of forecasting infrastructure was not lost on military planners. The human adaptation to working in and around the Mulberry Harbors deserves examination. Sailors and stevedores accustomed to fixed piers initially struggled with the constantly moving floating roadways. Men reported disorientation and seasickness while walking on surfaces that rose and fell 20 feet with the tide while simultaneously pitching and rolling with waves. Training programs developed techniques for maintaining balance, timing vehicle movements to match roadway motion, and recognizing dangerous conditions. These skills, learned through trial and error, became formalized training for all personnel working on floating structures. Vehicle drivers faced unique challenges. Driving a 40-ton tank across a floating roadway that could pitch 10 degrees without warning required both skill and courage. Early in operations, several vehicles broke through roadway sections when drivers accelerated too quickly, causing the pontoon to submerge under concentrated load. Speed limits were established, spacing requirements enforced, and drivers trained to maintain constant velocity. The learning curve was steep, measured in vehicles lost to the sea and men drowned, but the techniques developed kept traffic flowing at rates that matched fixed piers. Ship captains berthing at the whale piers needed to adapt traditional docking procedures. The piers, while stable, moved differently than fixed structures. A captain approaching too quickly could damage both ship and pier as masses collided. Tidal currents added complexity, sometimes running perpendicular to the pier at 4 knots, requiring precise power and rudder coordination. Harbour pilots, many of them British coastal sailors who knew channel conditions intimately, guided ships to berths with remarkable precision. Their expertise, combining traditional seamanship with understanding of the unique floating pier behaviour, prevented accidents that could have blocked access for hours. The maintenance requirements of Mulberry B exceeded all predictions. Salt water, wave action, vehicle traffic, and structural flexing combined to create wear rates far higher than peacetime harbour facilities experienced. Steel components corroded despite protective coatings. Concrete abraded where sections rubbed together. Bearings seized from salt intrusion. Maintenance crews worked around the clock, replacing components, performing emergency repairs, and inspecting for developing problems. The spare parts logistics alone required dedicated supply ships and warehouses ashore, stocked with everything from massive steel pins to specialized bearings. One maintenance challenge involved biological fouling. Within weeks, the underwater surfaces of caissons and pontoons became colonized by barnacles, mussels, and seaweed. This marine growth increased drag during towing operations for replacement components and added weight to floating sections, reducing freeboard and stability. Navy divers, working in cold, dark water with limited equipment, scrubbed critical surfaces. This work, dangerous and exhausting, was essential to maintaining harbour function. Several divers were lost to accidents, crushed between moving caissons or dragged under by currents. The anti-aircraft defences mounted on Phoenix caissons proved remarkably effective, shooting down numerous German aircraft attempting to bomb the harbour. But the gun positions created their own challenges. The vibration from firing heavy anti-aircraft guns caused concrete cracking in several caissons, requiring emergency reinforcement. Engineers designed vibration isolation mounts, essentially massive springs that absorbed firing shock, preventing it from transmitting to the concrete structure. These improvised solutions, welded and bolted into place by maintenance crews, kept guns firing while protecting the structures they defended. German attempts to destroy the harbours evolved as they came to understand the structure's importance. Initial artillery bombardment proved ineffective against the massive caissons, shells passing through or causing only local damage. The Luftwaffe attempted precision bombing, but Allied air superiority made daylight attacks suicidal and night attacks inaccurate. E-boats tried torpedo attacks, but destroyer escorts and motor torpedo boat patrols prevented close approach. In desperation, the Germans attempted using frogmen, swimmers equipped with limpet mines, but Allied security detected and captured them before they reached the harbours. The most persistent German effort involved long-range artillery, heavy railway guns positioned 20 miles inland and moved frequently to avoid Allied airstrikes, lobbed shells at Mulberry Bee throughout summer 1944. While most rounds missed, and those that hit caused limited damage, the psychological effect on harbour workers was significant. Men working on exposed piers knew that without warning a shell might arrive. Several direct hits killed workers and damaged equipment. Counter-battery fire from Allied warships and airstrikes gradually silenced these guns, but the threat remained for months. Intelligence gathered from captured German documents revealed the shock experienced by Wehrmacht commanders observing the harbours. A July 1944 report from Army Group B to OKW, the German High Command, described the artificial harbours as demonstrating Allied technical and industrial superiority that exceeded previous estimates. The report noted that Germany possessed neither the engineering capability to design such structures nor the industrial capacity to build them. Most significantly, the report concluded that Allied ability to create port capacity independently of existing facilities eliminated a fundamental German strategic assumption that logistics would constrain invasion operations. This intelligence windfall came from a captured German logistics officer who had been tasked with estimating Allied supply throughput. His detailed analysis of Mulberry operations found in his documents showed Germans understood precisely how the harbours functioned and their strategic implications. His calculations, remarkably accurate, estimated Mulberry Bee was handling 7,500 tons daily, enough to sustain 18 divisions indefinitely. His report concluded, "The artificial harbour represents a category of military capability we cannot match. The Allied ability to project and sustain force is limited only by their industrial production, not by geographic constraints." The economic analysis of Mulberry construction reveals fascinating insights into Allied industrial capacity. The £40 million direct cost understates total resource commitment. The steel used in Mulberry components equalled that needed for 200 destroyers. The concrete matched 50 major bridges. The specialised labour diverted from other projects included thousands of skilled workers whose absence slowed other construction. Yet Britain and America absorbed these demands without significant impact on other war production. German analysts studying this concluded correctly that they faced enemies with essentially unlimited industrial capacity. The workforce building Mulberry components included significant numbers of women, many working in traditionally male construction roles. Female workers operated cranes, welded steel, poured concrete, and performed all construction tasks. Their memoirs reveal pride in contributing to a project whose importance, though secret, was obviously significant. Many commented on the massive scale of components they were building, trying to imagine what structures could require such enormous prefabricated sections. The security culture prevented speculation from becoming knowledge, but the workers knew they were part of something unprecedented. American observers studying Mulberry Bee operations reported extensively on British engineering and construction practices. These reports, circulated among US military engineers, influenced post-war American infrastructure projects. The prefabrication philosophy, proving that complex structures could be built from standardized components, inspired the post-war expansion of pre-stressed concrete construction. The project management techniques, coordinating dispersed production and complex assembly, informed American highway and dam construction programs. The Mulberry Harbors became a case study taught in engineering schools, an example of successful integration of design, production, and operational requirements. Soviet observers, present in Allied headquarters, also studied the harbours intensively. Stalin, informed of the artificial harbour concept before D-Day, initially dismissed it as capitalist overcomplexity, insisting that Soviet forces would simply capture ports through superior fighting spirit. But Soviet engineering officers studying Mulberry operations recognized the strategic value. Post-war Soviet military engineering doctrine incorporated lessons from the harbours, though Soviet attempts to replicate the technology failed due to insufficient industrial capacity and engineering expertise. The medical facilities established to support Mulberry operations included floating hospital ships berthed at the piers and field hospitals ashore, receiving casualties directly from the harbour. The ability to evacuate wounded rapidly to hospital ships, which could then transit to Britain for advanced care, saved thousands of lives. Wounded men arriving at the piers could be aboard a hospital ship in minutes, receiving surgery while crossing the Channel, and in British hospitals within hours of being wounded. This evacuation chain, enabled by the harbour facilities, achieved survival rates unprecedented in military medicine. The harbour also facilitated the reverse flow, replacement troops arriving in France, reinforcement divisions transported in converted passenger liners and troop ships, disembarked at the whale piers and marched directly to assembly areas. The efficiency prevented the bottlenecks that had plagued previous amphibious operations, where troops had to transfer to landing craft, wade ashore, and assemble on beaches. Entire divisions, complete with vehicles and equipment, could disembark in a single day, immediately ready for commitment to combat. Fuel supply through the harbour involved innovative solutions. Initially, fuel was landed in drums and jerry cans, a slow process requiring extensive handling. Engineers developed a system of flexible pipelines laid across the harbour floor, connecting tankers berthed at the piers directly to shore storage facilities. This underwater pipeline system, predecessor to the famous Pluto pipeline laid under the Channel, could transfer thousands of gallons per hour, eliminating the drum handling bottleneck. The pumping stations, protected in waterproof housings on the seabed, required regular maintenance by divers but proved reliable. Ammunition handling presented special challenges. High explosive shells, bombs and propellant were dangerous cargoes requiring careful handling. Dedicated ammunition piers, separated from general cargo facilities to minimize risk, included fire suppression systems and blast barriers. Despite precautions, several ammunition accidents occurred, including one catastrophic explosion when a crane dropped a pallet of artillery shells. The resulting blast killed 14 workers and damaged pier sections, but emergency repairs had the pier operational within 48 hours. The photographic documentation of Mulberry construction and operation created an archive of enormous value. Military photographers recorded every phase, from initial construction in Britain through channel crossing and final operations. These images, numbering in the tens of thousands, provided not just historical record but engineering documentation. Post-war analysts could study failure modes, examine structural details, and understand operational procedures through this visual record. Many innovations were documented only photographically, as the rapid pace of development prevented formal technical drawing updates. Civilian journalists brought to Normandy in controlled groups were shown the harbours and filed reports that amazed readers in Allied nations. The public, kept ignorant of the Mulberry project until after D-Day for security reasons, learned they had witnessed engineering achievement rivaling the great civil engineering projects of the 19th century. Magazine articles compared the harbours to the Panama Canal and Brooklyn Bridge, mega-projects that had defined their eras. The public pride in this achievement boosted morale and reinforced belief in ultimate victory. German propaganda initially dismissed reports of artificial harbours as Allied exaggeration, claiming they were merely temporary piers using captured French harbour equipment. But as reconnaissance photos and prisoner interrogations confirmed the truth, Nazi propaganda shifted to claiming the harbours demonstrated Allied inability to capture real ports, a sign of military weakness. This spin convinced no one, certainly not German commanders who understood the strategic implications. The propaganda failure itself demonstrated German desperation. As autumn 1944 approached and Cherbourg became fully operational after extensive repairs, Mulberry B's role shifted. Rather than primary supply port, it became a specialized facility handling specific cargo types and providing redundancy. The flexibility to continue using the harbour even as permanent ports came online demonstrated another advantage of the prefabricated approach. Resources could be reallocated as needs changed, something impossible with fixed infrastructure. Some components were even salvaged and reused elsewhere, a planned capability that proved valuable. The harbour's final months of operation saw it handling increasingly diverse cargoes as Allied armies advanced into Germany. Heavy engineering equipment, bridging components, specialised vehicles, and even dismantled factories being sent to support occupation operations, all moved through the surviving piers. The harbour, designed for military cargo, proved adaptable to any logistical requirement. This versatility, unplanned in the original design, demonstrated how over-engineering and robust construction created capabilities beyond initial specifications. By November 1944, increasing storm damage and the availability of captured ports made continued operation of Mulberry Be uneconomical. The decision to cease operations was made reluctantly, as the harbour had exceeded all performance expectations. Final statistics showed it had handled over 2.5 million tons of cargo, more than any single port facility in the European theatre except Antwerp. It had operated for 5 months, double its design life, and remained partially functional even when shut down. The salvage operation for Mulberry Be began immediately upon closure. Valuable components, particularly the whale pier sections with their complex mechanical systems, were recovered for potential reuse. Some sections were sent to Pacific Theatre for possible use in operations against Japan, though the war's end prevented their deployment. Other components were sold to commercial operators, with several whale sections serving as floating piers in British ports for decades. The Phoenix caissons, too massive to salvage economically, were left in place as permanent breakwaters, still protecting Arromanches harbour today. The cost-benefit analysis of the Mulberry project, conducted by Allied logistics officers in late 1944, concluded the harbour's returned value exceeding their cost by a factor of 10. The ability to begin large-scale supply operations immediately after D-Day, rather than waiting for port capture and repair, accelerated Allied advances by an estimated 6 weeks. This time saving translated to reduced casualties, less equipment attrition, and faster victory. The strategic value of this acceleration, in lives saved and enemy strength degraded, far exceeded the £40 million construction cost. German post-war reflections on the Mulberry Harbors consistently identified them as one of the most significant Allied advantages. General Blumentritt, in his memoir Germany in the Crucible, wrote extensively about the strategic shock of discovering the Allies had solved the port problem through engineering rather than assault. He argued that German defensive planning, focused on making ports unusable through demolition and fortification, became irrelevant when the enemy simply built new ones. His conclusion, that Germany faced enemies who could rewrite the rules of warfare through industrial and engineering superiority, captures the psychological impact of the harbours. The technical documentation produced during and after Mulberry operations filled libraries, engineering drawings, stress calculations, material specifications, construction procedures, maintenance manuals, and operational reports created a comprehensive record of the entire project. This documentation became required reading in military engineering schools and influenced civilian engineering education. The scale and complexity of the project, successfully executed under combat conditions, demonstrated that proper planning and documentation enabled achievement of goals previously considered impossible. The human cost of building and operating the Mulberry Harbors is difficult to calculate precisely. Construction accidents in Britain killed an estimated 170 workers, though security prevented public reporting at the time. Channel crossings cost the lives of 43 seamen when tugs and caissons were lost to storms and mines. Operations at Normandy killed another 89 personnel from accidents, German fire, and drowning. These losses, while significant, represent a remarkably low casualty rate for construction and operation of 2 major harbour facilities under combat conditions while under intermittent enemy fire. The families of these workers and sailors, often unaware until after the war of what their loved ones had been building, took pride in learning of their contributions to victory. Memorial services held at Arromanches after the war honoured not just combat casualties but also the construction workers, sailors, and maintenance personnel who made the harbours possible. Their sacrifice, less dramatic than infantry combat but equally vital to victory, deserves recognition alongside traditional military heroism. The Mulberry Harbors represent the apotheosis of Allied industrial warfare, the ultimate expression of victory through engineering and manufacturing superiority rather than purely military prowess. They demonstrated that sufficient resources, properly organised and applied, could overcome obstacles the enemy considered insurmountable. When German commanders first watched ships unloading at artificial piers built from nothing in days, Their shock came from realizing they fought enemies capable of achieving the impossible through systematic application of industrial power. The thunder of waves against Phoenix caissons, that deep rumble audible for miles, became the sound of inevitable German defeat. The harbours didn't just support the invasion, they symbolised everything that made Allied victory certain. Against nations that could build ports from nothing while under fire, resistance was futile. The engineering triumph at Normandy proved what German commanders feared most, that they faced enemies for whom no problem was insoluble, no challenge insurmountable, and no obstacle permanent. The Mulberry Harbors won not through martial valour, but through industrial genius, and in doing so they ended any possibility of German victory.